Good day, my dear students. Today we're going to discuss all about seepage. So, seepage in soil mechanics is the movement of water in soils and often a critical problem in building foundations. Seepage depends on several factors, including permeability of the soil and the pressure gradient, essentially the combination of forces acting on water through gravity and other factors. So the difference between seepage and permeability is that permeability is a measure of how easily a fluid can flow through a porous medium, while seepage is the flow of water through soils or the movement of water through soils. So in seepage, we discuss all about flow nets. So the continuity equation in an isotropic medium represents two orthogonal families of curves, that is flow lines and equipotential lines. A flow line is a line along which a water particle will travel from upstream to the downstream side in the permeable soil medium. An equipotential line is a line along which the potential head at all points is equal. Thus, if piezometers are placed at different points along an equipotential line, the water level will rise to the same elevation in all of them. So figure 1 demonstrates the definition of flow and equipotential lines for flow in the permeable soil layer around the row of sheet piles. So for example, we have a sheet pile here, and this is a soil medium, and there is water above that soil profile. This is the upstream and this is the downstream. So yung ating tubig, yung water particle from this upstream magfo-flow mula dito papunta sa kabila sa downstream. And yung water particle daw natin may certain path na sinusunod sa pag-flow. So yung path na yun ay magabuo ng line. So yung line na yun is what we call the flow line. It is a line along which a particle or a water particle will travel from upstream side to the downstream side in the permeable soil medium. So, yun namang natawag nating equipotential line. This is also an invisible line in a soil profile na kapag nilagyan natin ng piezometer dito sa part na to at dito sa part na to, they will have the same pressure head even in this area basta sakop ng linya na ito. So yung ating flow line ay ito, flow line to, yung ating ground surface, and this is also considered equipotential line naman, yung babang-baba ng ating soil tissue. That is what we call equipotential line. Kasi kapag naglagay tayo ng piezometer dito, pareho din yung malabas na potential head natin. So, this is an example of a flow net. So, a combination of a number of flow lines and equipotential lines is called a flow net. Flow nets are constructed for the calculation of groundwater flow and evaluation of heads in the media. To complete the graphic construction of a flow net, one must draw the flow and equipotential lines in such a way that the equipotential lines intersect the flow lines at right angles. So for example, this is a flow net. Yung intersection between the flow line and the equipotential line, dapat daw yun ay almost at right angle. So, almost at right angle siya. Yan. Right angle yan. Yan. Almost at right angle siya. And then, the flow elements formed are approximate square. So, yung area bounded nung ating equipotential line and flow lines should be square. So, almost square siya. Itong area na to. And these are the area. Yan, square yan, square. Square yan malabas. So let's erase first the drawings. So that is the flow line. So I mean the flow net. So this is an example of a flow net. Again, these are flow lines here. And these are equipotential drops. So if you look at the figure, there is what we call kx equals kz and k. So a equals k. So yung kx and kz, these are the flow or the coefficient of permeability or the hydraulic conductivity at horizontal and vertical direction. So, yun kasing ating lupa, 'di ba? Kapag 3D natin 'to, meron pa siyang 3D. Meron dito sa likod kunwari nitong drawing natin na ito, 3D natin 'to. Yung tubig natin, syempre, mag-flow siya from here papunta dito and meron ding yung tubig natin mag-flow papunta sa Z direction. So, may X and Z direction yan. I'm sorry, mali but that should not be like that. Pag ganun siya, rather. Magpo-flow siya pag ganyan, yung ating tubig, magpo-flow papunta dito and pa-flow papunta doon. So, kaya ito yung tinatawag na KX natin. Itong line na ito, yung direction nito and yung flow ng tubig papunta dun sa direction na yun is what we call KZ. So, in this case daw, Kx is equal to Kz equals K. Ang tawag doon is isotropic soil. So, pag sinabing isotropic soil, lahat ng flow ng tubig is equal at any direction, even if it's horizontal or vertical. So, if you look at the figure, NF is equal to 4. How are we going to determine the flow line? If we count the flow line here, ang flow line lang dyan is 1, 2, 3. So, 3 lang siya. Paano siya naging 4? This is the groundwater. The ground surface is also a flow line. Kaya, pag pinilang mo, kasama yung ground surface. So, ang technique para mabilang natin kung gaano kadami yung lines, we have to get the count the spaces rather. So we have to count the spaces. Say for example, this is 1, this is 2, this is 3. So, and this is 4. Ito yung spaces. So 1, 2, 3, 4. That's why NF is equal to 4. For equipotential drop naman, ganun din. We also count the spaces. Kasi, di ba, if we count the lines lang, there are 1, 2, 3, 4, 5 lang. But if we itong line na to, this is also equipotential drop. Or equipotential line rather. So, if we count the equipotential line, and the spaces, ika-count natin, this will be, I'm sorry, that should be 1. Nagsimula kasi dun sa paper line na lang. This will just be equal to 1. This is 1, 2, 3, 4, 5, and 6. Therefore, there are 6 equipotential lines in here. Okay. So, how are we going to compute for the seepage calculation? seepage rather. In any flow net, the strip between two adjacent flow lines is called a flow channel, and the drop in the piezometric level between any two adjacent equipotential line is the same. This is called the potential drop, and seepage in a flow net can be determined using the formula Q equals K H and F over ND. What is H? Total head loss. And NF and ND are number of flow channels and potential drops, respectively. And what is K? This is the coefficient of permeability or the hydraulic conductivity. How are we going to determine H in the flow net or in the sheet piles or in the dams or weirs? So H here is the difference between water levels. So if you look at this one, this is the upstream level and the downstream level. So H is the difference between the ground, two water levels here. So this is H. This is the difference between the two water levels. Therefore, it is equal to H1 minus H2. That would be H in that figure. We also have what we call anastrophic soils or non-isotropic soils. So yung sinabi ko nga na magkaiba yung permeability sa horizontal and vertical direction. Magkaiba yung Kx at Kz. So in nature, most soils exhibit some degree of anistropy or anisotropy. So pag sinabing anistrophic soil, hindi man pare-pareho yung flow ng tubig in all directions. So magkaiba yung Kx natin and Kc. To account for soil anisotropy, with respect to hydraulic conductivity, the flow net construction must be modified. So the rate of seepage per unit length in anistrophic soil can be calculated using Q equals square root of Kx multiplied by Kz multiplied by H and F over Nd. In order for us to understand more of the topic, let us first solve this problem. So the section of a sheet pile is shown in the figure below. The coefficient of permeability of the soil is 4.2 times 10 raised to negative 3 meters per second. So we are to determine the seepage into the downstream side per meter length of the sheet pile. So if you look at this one, this is an example of a flow net, a sheet pile here, and the upstream and downstream level. So if we compute it, this is the solution. So, in the problem, there's no given value of kx and kz. And that means there is only one coefficient of permeability. That means it is an isotropic soil and the flow of water through vertical and horizontal direction is the same or in all directions. And then we calculate H and determine the number of flows and the number of flow line rather and the number of equipotential line or potential drops. So in this form, in this figure, we have to determine H, and H is the difference between the upstream level and the downstream level. So if we compute it, it is the difference between 7 and 2. So H or the head difference is equal to 5 meters. So K is given, that is 4.2 times 10 raised to negative 3 times 5. And how are we going to determine the number of flow lines? So again, we count the spaces between the flow lines. That is 1, 1, 2, 3, and 4. So therefore, NF is equal to 4. And we determine the number of equipotential lines. So we count again the spaces. 1, 2, 3, 4, 5, 6, 7, 8. Therefore, there are 8 equipotential lines here or equipotential drops. So, by substituting it to the formula, this will give us 0.0105 cubic meters per second per meter. Okay. Sample number 2. A section is shown, and the hydraulic conductivity of the permeable layer in the vertical and horizontal directions are 2 times 10 raised to negative 2 millimeters per second and 4 times 10 raised to negative 2 millimeters per second, respectively. So we are to calculate the seepage loss of the dam in cubic meters per day per meter. So if we're going to look at the problem, this is an example of anastrophic soil or non-isotropic soil because there are two given hydraulic conductivity at Kx and Kz. So therefore, Kz is equal to 2 times 10 raised to negative 2 millimeters per second. And in the problem, we are required to get the seepage loss in cubic meters per day per meter. So we have to convert this millimeter per second to meter per day. So 2 times 10 raised to negative 2 millimeters per second is equal to 1.728 meters per day. And Kx is equal to 4 times 10 raised to negative 2 millimeters per second. That is equal to 3.456 meters per day. So if we determine the number of equipotential lines, so the number of equipotential lines is we count again the spaces between the equipotential lines. So this is 1, 2, 3, 4, 5, 6, 7, 8. So therefore, n is equal to 8. And in the problem, it is already given that there are 2.5 flow lines because the lowermost flow channel has a width to length ratio of zero point 0.5 only. So that's why in the problem, the number of flow lines is just 2.5, not 3. So by substituting the values in the formula, Q equals square root of Kx, Kz times H NF over ND, we get the value square root of 1.728 multiplied by 3.456 multiplied by 6.1. Why 6.1? It is the head difference. So the head difference is 6.1. It's already in the figure. Multiplied by NF is 2.5 over 8, and that is equal to 4.66 cubic meters per day per meter. Okay. For sample number 3, the section of coffer dam is as shown in the figure. If the coefficient of permeability of the soil is 5 times 10 raised to negative 3 meters per second, we are to determine the seepage into the ditches per length of the coffer dam. So if we look at the figure, there are two sheet piles here, and the left side and the right side are identical. So, mirror lang siya nung kabila if you look at this one. So, if we were going to analyze this problem, pwede nating unahin muna itong part na to, and then just by multiplying it by 2 kasi pareho lang naman yung flow lines, yung number of flow lines and equipotential lines natin. We just multiply Q by 2. We're going to get the seepage into the ditches per length of the cover dam here. So let's solve it. So say for example, in the example is there are no given Kx and Kz. That means there is only one K or coefficient of permeability, and we're going to use Q equals KH and F over ND. If we're going to determine H, it's the difference between the water level. So 38, this is elevated at 38 meters. And the elevation here is 18 meters. This is the second water level. So 38 minus 18 is 20 meters. That is H. K is already given. That is 5 times 10 raised to negative 3 times 20. How are we going to determine the number of flow lines? Again, we count the number of spaces. 1, 2, 3. That's why NF is equal to 3. We count the number of spaces again in equipotential lines. 1, 2, 3, 4, 5, 6, 7. That's why there is 7 here, which will give us the answer 0.040 cubic meters per second per meter. That is just for this part sa kalahati. Kasi meron ding magpa-flow ba dito, upstream side pa rin siya. So if we analyze again, this is also 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7 also. That's why this is these are two identical sides, and we're just going to multiply what we have already solved by 2, and will give us the seepage loss in this coffer dam, and that is 0.086 cubic meters per second per meter. And that will be the answer for this problem. Okay? And lastly, in seepage, we have what we call uplift pressure under hydraulic structures. Flow nets can be used to determine the uplift pressure at the base of a hydraulic structure. This general concept can be demonstrated by a simple example. So in this figure shows a weir, the base assuming, I'm sorry, the base of which is 2 meters below the ground surface. The necessary flow net has also been drawn, assuming that Kx is equal to Kz equals K. The pressure distribution diagram at the base of the weir can be obtained from the equipotential lines as follows. So if we look at the figure, there are 7 equipotential drops. So let's count the spaces. 1, okay, let's 1, this is 1, 2, 3, 4, 5, 6, and 7. That's why there are 7 equipotential drops or ND. And the difference in the water levels between the upstream and downstream side is equal to 7 meters. So 7 meters. So the difference between upstream and downstream side is 7 meters. So if we're going to determine the uplift pressure at A, at this equipotential drop, we have to determine the pressure head at A multiplied by the unit weight of water. So what is the pressure head at A? This is the water level. So magsimula tayo dun sa upstream level. So 7 plus 2, yung point A natin is located 2 meters below the ground surface. So 7 plus 2 siya. Tapos, isusubtract natin yung head loss dun sa potential line na yun. So, we already got the head loss in point A, that is 1 meter. Per equipotential line, may head loss tayong 1 meter. So, at first equipotential line, ang head loss natin is 1 meter. So, 7 plus 2 minus 1 is that multiplied by unit weight of water is equal to 8 unit weight of water. So, for letter B here, this will be equal to 7 plus 2, that will be 9, minus, this is the second equipotential line, that's why there will be 1, 2. So, 2 times ang head loss per potential drop is equal to 1 meter. That's why, imumultiply natin siya by 1. This will, and then multiply all in all by unit weight of water. This will be 7 multiplied by unit weight of water. Sa C naman, say for example sa C, this will be 9 minus 3 times 1 times unit weight of water. So this why this will be 6 times unit weight of water, kilonewton per meter squared. For letter D, This will be quantity 9 minus 4 times 1 multiplied by unit weight of water. That's why this will be 5 unit weight of water. And then for letter E, this will be 9 minus 5 times 1 multiplied by unit weight of water, which will give us 4 times unit weight of water. And for letter F, at that potential line here, equipotential line rather, this will be 9 minus 6 times 1 multiplied by the unit weight of water equals 3 times unit weight of water. So class, hindi man laging 1 ang imumultiply. So we have to divide head loss over the number of equipotential lines. That's why kumuha tayo na nagkataon na yung H natin is 7 and there are 7 equipotential lines. 7 over 7 is equal to 1 meter. So kaya naging 1 meter yan. Pwede siyang magbago. Not always 1. Okay? So that would be the uplift pressure at any point in this dam at certain points here rather. And how are we going to determine the uplift force? So the uplift force per unit length measured along the axis of the wear can be calculated by finding the area of the pressure diagram. So we're going to determine the area of this one. Kasama yung 8 rather. We're going to determine the area of this one para makuha natin yung uplift force. So how are we going to determine that? That's just equal to uh, this side, then this side over 2 multiplied by the length multiplied by the unit weight of water. So that will be the not you don't have to multiply it by unit weight of water, just by 1 meter length. That will be the uplift force. So this will be the area. The area of this one is 8 plus 3 over 2 quantity 14, that would be multiplied by 1, that would be the force. Okay, so that would be all, and that's the uh, end of our topic for this day. And if you have any question, you can always contact me personally. And thank you everyone for listening. And I hope you learned something from this lecture. And I hope to see you next time. Good day. Thank you. Bye.